Good evening, everyone. My name is Shiqiang, Huang, and I'm a PhD student from MICE. And thanks for being here and listen to my talk. I know most of you are more like a Miro or a rock person, but tonight this talk will be a little bit different. I'm going to introduce you guys a really cool and new Miro dating technique, and hope you guys enjoy this talk and can get something from this talk. Okay, I will continue this talk. So why we care about mineral deposit dating? As the exploration geologist, the goal for us is always to look for the mineral deposit with the knowledge we have. I think so. What kind of knowledge should we have? I think it should at least include the knowledge about the mineral deposit model and associate the exploration strategy. So, and the age of the mineralization and alteration are arguably one of the most important information for both all deposit models and mineral deposit exploration. And this is because the development of robust all deposit model depends on the reliable age constraints for alteration and mineralization, and the timing of the alteration and mineralization relative to the tectonic events. And the geological history of the host sequence is important to the exploration models. So dating the mineral deposit is important for us. Basically, there are two ways to date a mineral deposit. One method is called the relative dating. For example, we can use the cross-cutting relationship of the geological bodies, to date a mineral deposit. It's like, for example, we can say, oh, this mineral deposit is later. Based on the cross-cutting relationship, we can say this mineral deposit is later than the Triassic period, but earlier than the Cretaceous period. So this method gives you a relative age. So this is called the relative dating method. And another one is the absolute dating method, like the radiometric method. And today we are going to talk about the absolute dating method. And specifically, we are going to talk about the in-situ rubidium and strandchain dating method. And before we go into, before we talk about the rubidium and strandchain dating, I would like to give you guys a quick review about the isotope. So as we know, every atom contains a small nucleus surrounded by a cloud of electrons. So this is nucleus and surrounded by the electron. And the nucleus is composed of the protons and neutrons. And the number of protons determines what elements this atom is. For example, in this atom, it has 1, 2, 3, 4, 6 protons. So this is so we know this is the carbon atom. And the atomic mass number is decided by the number of neutrons and the number of protons. And for this atom, we have 6 protons and 6 neutrons. So this atom, it has the atomic mass of 12. So this is carbon 12. And isotopes are atoms of the same element with different numbers of neutrons. These are 3 atoms, and they all have 1 protons. So they all belong to hydrogen, but they have different neutrons. So there are different isotopes of hydrogen. For example, this one doesn't have a neutron, so the mass number would be 1. So this is called hydrogen 1. And this has 1 proton and 1 neutron, so the mass number will be 2, 1 plus 1. So it's hydrogen 2. And this has 1 proton and 2 neutrons, so this has mass number 3. It's called hydrogen 3. So they are all hydrogen isotopes. Okay, so in the textbook or the literature, you can always see something like this. And the 87 means the mass number is 87, and 37 is the proton number. It determines the element, rubidium. Okay, let's go back to rubidium and structure dating. And rubidium has two naturally isotopes. One is rubidium 85, the other one is rubidium 87. Between these two, rubidium 85 is a stable isotope. So when I say stable, it means it doesn't decay over time. And rubidium 87 is a radioactive isotope. This means like this isotope will decay over time. And strontium has 4 isotopes, 88, 87, 86, and 84, and all of which are stable isotopes. So the story between rubidium and strontium dating happens between rubidium 87 and rubidium and strontium 87. And rubidium 87 will decay slowly to strontium 87 over time. And because we know the decay rate of this decay system, so if we know how much rubidium has been decayed to strontium, we can back calculate the age of the system. So this is how this rubidium strontium dating works. And so what can we do with rubidium strontium dating? This method can be used to date the potassium-bearing minerals or rocks. Why is that? Because the ionic radius of rubidium is really similar to the ionic radius of potassium. So this allows rubidium to substitute for potassium and goes into the potassium-bearing minerals or rocks. As shown in this diagram, we can see that the rubidium concentrations has a really good correlation with the potassium concentrations in a series of rocks. Yeah, so we can use this technique to date the potassium-bearing minerals. Why? Oh, okay. Yeah. And the ability to date potassium-bearing minerals makes rubidium strontium dating a really attractive tool in the research of economic geology. This is because the potassium-bearing minerals like micas, like ironite and adularia, and micas like biotite or muscovite and some feldspar, they are really common alteration minerals in many types of many deposit types like porphyry, epithermal, organic, VHMS, skarn, gypsum, and pegmatite deposit. So if you can date these potassium-bearing minerals, you can use this data to constrain the alteration and mineralization age of the mineral deposit. So indeed, the rubidium strontium dating is has been used extensively in the past, especially from the 80s to 2000 years. However, in the past 2 decades, fewer and fewer people use this technique. It's kind of like people just don't like this technique anymore. So what's the reason for that? Okay, the main reason is because the traditional mass spectrometry cannot distinguish rubidium 87 and strontium 87. If we want to talk about it, let's take a look at the traditional mass spectrometry first. Oh, is it okay? Yeah. Okay. This is adjuvant 1700 ICP-MS. ICP-MS stands for inductively coupled plasma mass spectrometry. And this is the schematic diagram of the ICP-MS. And so how does this work? First, the sample will be introduced into the torch, and in this case, the instrument will produce a fireball called plasma. The temperature is really high for plasma. It could be 10,000 Kelvin for the temperature of the plasma. And this is a place all the material will be ionized. And then all the ions will be directed into a series of lenses and then go into the quadrupole. Quadrupole is a mass filter. And in the quadrupole, ions with different mass will be separated and measured one by one. For example, there will be ion flow with different masses going to the quadrupole, and only ions with the same mass will pass through the quadrupole by one time. And for example, there are tons of the ions flow going to the quadrupole. And if we set the quadrupole to be mass 206, so only will be the light 206 will pass through the quadrupole and be measured by the detector. So this is how it works. Okay, so as we mentioned before, the rubidium and strontium dating is a beta decay system. Rubidium 87 will decay to strontium 87. So if we want to date using the rubidium strontium dating method, we need to measure the signal of rubidium 87 and strontium 87. So I want you guys to think about, if we want to measure the signal of these two, what will happen with the traditional mass spectrometry? Anyone? Yeah, because the problem with the traditional mass spectrometry is they cannot distinguish the isotopes with the same mass. For example, we want to measure the rubidium 87 and strontium 87, but they have the same mass. So they will all pass through the quadrupole and being measured by the detector. This means the instrument cannot distinguish which one is rubidium 87, which one is strontium 87. So the signal are overlapped. So that's why the traditional mass spectrometry, they cannot they cannot distinguish rubidium 87. And that's why the traditional rubidium and strontium dating is a bulk sample method. When I say bulk sample method, this means if we want to date the hydrothermal biotite, we need to for example, this is a porphyry sample. If we want to analyze the hydrothermal biotite, we need to do the mineral separation first. And then we need to dissolve all the biotite separate and dissolve into the solutions. And then we need to do a lot of a series of the wet chemistry to separate the rubidium and strontium. And then and the final step is to be analyzed by the mass spectrometry. So as we can see from this complicated process, we can know the traditional rubidium and strontium dating is a really labor intensive and time consuming and expensive method. And because if we want to calculate ascron date, we need several samples. So probably at least 10. So it means you need to repeat the whole process 10 times. So it's a really, it's not a good method. And in addition to this, the traditional method has many limitations in the mineral deposit dating. I will give you an example of this. Okay, we all know porphyry deposits has extensive potassium alteration, like the hydrothermal biotite and hydrothermal K-feldspar. And these potassium alteration minerals, like, come on. Oh, the potassium alteration minerals like biotite, they usually occurs as fine grain as replacement of the previous magmatic biotite. As we can see here, this dark brown one, fine grain biotite, they are the hydrothermal ones, and the light brown ones, they are this is the magmatic biotite from the porphyry. After the formation of the hydrothermal biotite, they are easy to be altered or welded into chlorite or some other minerals. If we want to date the alteration age, we need to only separate the hydrothermal biotite out of this rock. So I don't know if you guys have done the mineral separation before, but this is almost impossible to do that. You know, it's so fine grain. This is 100 micron. Yeah, you just imagine you need under the microscope, you need to separate this out. That's just impossible. So the traditional method cannot exclude the altered or the welded part of the mineral separate. It's also difficult to separate different generations of the minerals. And plus these disadvantages. So all this lead to the rubidium extraction dating to be abundant in the mineral deposit dating. But right now, with the new generation of the triple quadruple mass spectrometry, the rubidium extraction dating may become attractive technique again. So what is special of this new instrument? This is actually 8900 SP MS. Different from the traditional single quadruple mass spectrometry, and the new generation one, it has one reaction cell sandwiched by two quadruples. So this configuration allows online separation of rubidium extraction and solve the issue of the isobaric interference. Let's take a look at this diagram here. First, we can set the first quadruple to be mass 87 and let both rubidium 87 and strontium 87 to pass this quadruple. And at the same time, we can reject all the ions, apart from mass 87. Then in the reaction cell, we can input or filled with some reaction gases like oxygen or natural oxide. And with these reaction gases, rubidium strontium will react with these gases and react into strontium oxide. At the same time, rubidium doesn't react with these gases. It will stay at the same mass. So it will still be the rubidium 87. And then we can set the second quadruple to be 103, which is the mass number of the strontium oxide. So by doing this, we can reject the rubidium 87 and only let the strontium 87 strontium oxide to pass through the second quadruple. And by doing this, we can achieve the online separation of rubidium and strontium in the mass spectrum spec. Okay. And then we can solve the isobaric interference in this new type of mass spectrometry. And then if we can connect the instrument to the laser ablation system, we can achieve the in-situ rubidium and strontium dating. And basically, I mean, the laser ablation, we just use laser to shoot on the mineral surface and to produce the